Okay, let's continue and talking about alpha decay and positron emission. Okay, so let's do positron emission first. This is very similar to beta decay, but instead of going from a neutron to a proton, we're going from a proton to a neutron. Okay, and when we do this, we emit a positron, which is the same mass, essentially, which is practically none, especially compared to a proton and neutron, of an electron, but it has a positive charge instead of a negative charge. Okay? So something to be mindful of. We have a similar interaction. Okay? So we're starting with oxygen, which has a mass number of 15, right? And we know that this is the number of protons, which is 8 for oxygen, plus the number of neutrons there. So we'd have 7 neutrons, okay? But we're going to take one of these protons and we're going to turn it into a neutron. So that means we're going to lose a proton. So instead of 8, we're going to have 7. And then it's going to turn into a neutron. So instead of 7, we'll have 8. And again, we end with a mass number of 15, and that's what we see. And then we go, okay, the number of protons went from 8 to 7. Atomic number 7 is associated with the element nitrogen. And then that positron emission is this positron, okay? Mass similar to an electron, positively charged. Again, conservation of mass, and I think charge as well. Like we have 15, 15 plus 0, 8, 7 plus 1. Okay. Now, our last type is alpha decay. Alpha decay is emitting an alpha particle, and an alpha particle is a helium nucleus, essentially. It's 2 protons and 2 neutrons. Okay, they don't have any electrons that they take with them. They are a positively charged particle. And so we have our helium nucleus, which is alpha decay. Okay? And see that we have mass number of 226, and then on this side we have 222 plus the 4, and so this mass number is conserved. We have 26 on this side, or sorry, 226 on this side, 226 on that side, and then similar we have 88 protons, and then we have 86 plus 2 more, and so we still have the same number of protons. Awesome. Now, reminder, positron emission takes a proton and turns it into a neutron. So it allows us to decrease our number of protons and increase our number of neutrons. And so these elements down below give us that positron emission, and then up above, when we want to reduce the size of the element, both in protons and neutrons, then we're having alpha decay of these heavier, more massive elements. Typically, when an atom goes from a parent radioactive isotope to a stable daughter isotope or atom, we are left with electrons for the daughter that are in excited states. They have higher energy than normal. So what I mean by that is, remember when we were talking about the Bohr model and we have the different energy levels? Well, typically when we make this transition in any type of these decays, we are left with electrons that are in higher energy levels, and that they're going to make that jump back down to lower energy levels in order to stabilize. And when they do that, they emit an EM wave, which is sometimes in the visible light range, but these ones tend to be in these high energy levels and making these big jumps down, so we get these super tiny wavelength, high energy electromagnetic waves, and we'll see that in the form of gamma rays or X-rays. Something interesting to note is that we can determine if the type of radiation or decay that's occurring is an alpha or a beta or a gamma, because we can pass those particles through a magnet. And if we have this magnetic field running from north to south, the alpha particles, because they're positive, deflect up, and then the beta particles, because they're negative, deflect down, and then this gamma, which is neutral, it's just an electromagnetic wave, it's not positive or negative, it doesn't interact with the magnetic field, so it just goes straight through. Okay. We can have spontaneous emission, and we see this definitely in this like radioactive decay, where it's constantly happening and it's spontaneous. And then we can have this induced emission, which is like we're forcing it, we're sending a neutron to a big uranium nucleus, and we're splitting that nucleus, and we're forcing that to happen. And so this separation into smaller components can either be spontaneous, which is typically radioactive decay, or it can be induced. Like we were saying before, conservation of mass needs to apply. So our mass numbers need to be accounted for on the radioactive isotope side, as well as what it produces, the daughter, in whatever type of emission we're working with. Okay, so here's some examples of that. Let's work with this. A radioactive isotope has a mass number of 226 radium, and it has an atomic number of 88. And it's going to emit an alpha particle, okay? All right, so let's write out this nuclear equation. So we're starting with radium, isotope 226. And we know that one item that's going to be produced is that alpha particle. And the alpha particle we represent as a helium nucleus that has a mass number of 4 and an atomic number of 2. Okay, so we have 2 protons, and then we have 2 neutrons, which added together gives us a mass number of 4. And mass needs to be conserved. Whatever we have on the right, we also have to have on the left. Okay, so if this is 226, and then we have 4 here, we need to go, what do I need to add to 4 to get to this 226? So we'd have a mass number of 222. And then 88 and 2, so what do we have to have here to add to 2 to get to that 88? 86. And then the last part of this is saying, but what is this symbol? Let me go grab a periodic table. One moment, I'll be right back. So we have atomic number 88 is radium, but now we're going to go down to 86, which is radon. Okay, so we have an element symbol of Nr. And that's our nuclear equation. We have mass conserved on the top and the bottom there. Okay, now we have an unstable isotope of lead-209. It's going to emit a beta particle and an antineutrino. Okay, so we're starting with lead-209. And we're going to emit a beta particle. So that's our -1 and 0 there. And then we want to know what we have conserved here, right? And so if we have 209 and 0, then this must also be 209. 209 plus 0 would be 0. And then we'd need something plus a -1 to get to the 82. So if I have 83 minus 1, that would give me the 82. And then I'm going to go to my periodic table again. and I'm looking for atomic number 83. Bismuth, okay? Now a reminder, this can also be represented like that, okay? You can write out that an electron and an antineutrino were formed, right? So like instead of writing like this, I could also have done 209, 83 bismuth along with an electron plus an antineutrino. And then our last one, RB 37, rubidium 87 undergoes radioactive decay to strontium, I believe, yep, 87. Okay, so we have 87, 30, rubidium, and we're going to decay to strontium 87. Okay, I'm going to go to my periodic table. I'm going to find strontium, and it has an atomic number of 38. So I need to go, what type of decay should I have in order for mass to be conserved? Because if it's 87 here, 87 there, well, it's not going to be an alpha because I need a mass number of 0. And then this is one bigger than that one, so it must be a -1. So this must also be a beta emission. And again, I can write that like this, or I can write it as there's the electron plus our antineutrino there. Right. Okay. So, radiation penetrating power. It's an interesting phenomenon here. Where we at time-wise? Okay, perfect. All right. So, we have 3 types of radiation that we're going to focus on for this: alpha, beta, and gamma. Okay. Alpha particles, they were that helium nucleus. They're relatively big, especially compared to the other types. And because of the size, they can easily be stopped. They can be stopped by like a piece of paper or your skin. But if they're already internal, like in radium, and have you ever heard of the radium girls? Such an interesting story. I highly suggest that you look it up. These radium girls were painting watch dials, and they would stick their paintbrush in their mouth to make the tip of the paintbrush really fine. They'd dip it in the radium paint, and they'd paint it on, and then they'd put it in their mouth again to make it a fine point. And so they were ingesting, they were consuming some of this radium, which was emitting alpha particles, and it did a lot of damage. And so once it's internal already, alpha particles cause a lot of damage. And I think, again, it has to do with like that size of the particle. Now, beta is kind of in the middle here, that it has greater penetrating power than the alpha does. It's essentially a free electron, smaller, so it's easier to get through, like it gets through paper and things like that. But it doesn't do as much damage as like an alpha particle does. And then gamma is on the end of that spectrum. It's essentially massless. It's an electromagnetic wave that contains energy, and it can penetrate through even like lead. And so it has this great penetration power, and it does interact and can cause problems, but not nearly to the same degree as like beta and definitely alpha.